So we've learned about using naming systems for basic alkanes, alkenes, and alkynes, but there's a little bit of a twist when it comes to working with these. And so I think the best way to describe it is to actually take a look at them. Here I have an alkane, here's an alkene, and here's my alkyne. And so when it comes to actually naming these different molecules, we talked about all those rules, but alkenes specifically have a little bit of a trick to them. You see, an alkane has a single bond, and due to that single bond, the atoms attached to it actually have the ability to rotate freely 360 degrees, and they rotate constantly. But as soon as a molecule has a double bond, it no longer allows for any rotation. So we actually then need to think about the direction and the placement that things are attached around this double bond. Now, with a molecule that has a triple bond, it's actually not an issue. There's only one spot for molecules or for other atoms to actually attach around this triple bond. But hopefully this will make a little bit more sense as I show you an example using our double bond. So this is an example of a molecule with a double bond. And if we wanted to draw what this molecule looked like, I'm just going to draw it up top. You would have carbon, double bonded, and then another carbon group. And so if you wanted to come up with a name for this thing, I'm just going to push it over here like that so it's out of my way. What we would end up getting is 2-butene. But because there is no movement around this double bond, you can actually, let's just do something quick here. We're going to swap where these things are. So now I have my double bond, but those two carbons are actually attached on other opposite sides of that double bond. So now I have a molecule that looks like this. And according to what we've gone through so far, it would be called 2-butene. See, in organic chemistry, a molecule behaves based on its structure. And so we just saw two separate molecules because they have two different structures. But also in organic chemistry, molecules can never only have one name. And so we need a way to actually differentiate between these two molecules. They both cannot be called 2-butene. So the way that we do this is using a system that is called cis and trans. You see, cis means same side. And so, or actually it really just means same, but in organic chemistry, we often think about it meaning same side. So I want to take a look at this example up at the top for a moment. So this is our molecule that looks like this. You see, if we were to divide this molecule along the double bond, the chain of carbons actually continues both on the same side of that double bond. And to show you here, let's just pretend we were to split this in half. Then we would have hydrogens only on the top, but our molecule continues with carbon chains on the same side. That means that this is actually called cis-2-butene, showing that the double bond is in the 2 position, but the other carbons in that molecule continue on the same side of the double bond. So then let's take a look at this example. So in this molecule, if we were to do that same thing, if we take a look at our molecule, if we were to divide it along the double bond, then what you end up seeing is that the carbon chain continues on opposite sides of that double bond. You could see the same thing if we drew that little line, dividing the two like this. That chain continues on opposite sides. What that means is this is a trans molecule, meaning that the carbon chain continues on opposite sides of the double bond. So this would be called trans 2-butene, meaning we have a 4-carbon molecule with a double bond in the 2 position. The carbon chain continues on opposite sides of the double bond. Cis 2-butene and trans 2-butene are what we call stereoisomers. And stereoisomers you get with something like a double bond, where you have the same atoms connected in the same order, but in a different position. So that's what we mean when we talk about stereoisomers, is having the same atoms, the same order, but a different position. So cis 2-butene and trans 2-butene are great examples because you have the same atoms, CH3, CH2, CH2, CH3, CH3, CH2, CH2, CH3. But because of the connection around that double bond, and because that double bond is not able to rotate, the connection around that double bond changes the position and creates a stereoisomer. So when it comes to stereoisomers, really what we want to do at this level anyway is we want to be looking for the longest continuous chain of carbons and decide if it's continuing on the same or on opposite sides of the double bond. And that will help us figure out how to name it. The cis or trans goes at the very beginning of the name. And I know that may seem a little bit weird, but we're actually going to put that right at the beginning. Then we will name the branches. Then we will add our main chain after. So let's work through some examples. Okay, so here we have this molecule. We want to figure out what would we name this molecule. We're going to start like we normally start. So let's figure out the longest chain of carbons. There goes 1, 2, 3, 4, 5. That's my longest chain. So I'm dealing with some kind of pent. It has a double bond, so pentene. Pentene has the double bond in the 1, 2 position. But now we need to figure out, is this cis or is this trans? So one of the ways that I like to do this is to draw that line through my double bond in the same direction as the double bond. And then take a look, okay, my carbon chain is up here and is up here. They're both on the same side, cis. This molecule is cis 2-pentene. Okay, so that's a fairly simple example. Let's try another example. So here's our next example. I know this may look very similar, but you'll notice there's a little bit of a difference. It's drawn differently than we had our last one. So if we're going to name this, same as always, count your longest continuous chain of carbons. So 1, 2, 3, 4, and 5. Pent. Double bond. Pentene. Position of the double bond is either the 1, 2 or the 1, 2, 3. It's got to be in the 2 because that's the lower number. Now we need to figure out cis or trans. So I'm going to just do this for now so we can see. Chain of carbons continues down here. Chain of carbons continues up there. That is on opposite sides. Opposite sides of the double bond is trans. So we have trans 2-pentene. So you can see those are stereoisomers of each other. The only difference is the location of the continued carbon chain after. So let's try another example. All right, example number 3. So now we're looking at something quite different than what we had seen before. And we want to figure out what's our longest chain of carbons. So we have 1, 2, 3, 4. That's going to be my longest chain. Now, if you went 1, 2, 3, 4 like this, you can't do that because it didn't contain the double bond. When there's a double bond, you must count the longest chain that includes the double bond. So even if there's a longer chain that goes around the double bond, you can't use it for your main name. So we have 4 carbons. That's going to be bute. Double bond, butene. Position of the double bond is in the 1. Okay, now you may be thinking, okay, cis or trans, but let's do what we've done before. We want to take the longest part that's continuing after, so here, and there is no carbon over here, which means there is no possibility for this to be a stereoisomer. So we actually do not have to worry about cis or trans if the double bond is in the one position. If the double bond comes at the very first carbon, there is no chance for it to continue before or after because there is no before. So then to finish up the name, all we need to do is name this branch. And this branch is in the 2 position, right? Carbon 1, carbon 2, and it's a 1 carbon branch as a methyl. So we have 2 methyl, 1 butene. So there is my name for this molecule. Now, we've done some naming. I think our next example, we should probably draw one from the name. So let's try that. So here is the name we've been given, cis-2-methyl-3-nonene. And I think it's important to make sure we break down what everything means in the name so that we can figure out how we would draw this. So the first thing is I know non means a 9-carbon chain. That is going to be the longest chain in this molecule. And this chain has a double bond, and that double bond is in the 3 position. We also know, based on this name, that that double bond and that chain continues on the same side of the double bond. And in the 2 position, there is a 1 carbon branch. So we've broken down basically what this name tells us. We have a 9-carbon chain with a double bond in the 3 position where that 9-carbon chain continues on the same side after the double bond. But in the 2 position, we're going to find a 1 carbon branch as a methyl group sticking off. So now that we've broken down the name, let's draw it. When it comes to drawing these, I personally like to start with the double bond. I know it's in the 3 position, so I'm going to leave a little bit of room on this side. But I like to draw my double bond because it helps me deal with the cis and trans first. This is cis. So what that means is I need to draw my chain so that it continues on the same side before and after. And now I need to think, okay, if this is actually the 3 position, then I need 2 here. I'm just going to write it up here, actually. And that means there's 1 more carbon. So 1. So now I have 1, 2, 3, 4, 5. I need 9 in total. So 6, 7, 8, and 9. And I always like to double check. So 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Now, if you're doing this, you don't actually have to label the numbers, but I'm just doing this because it's an example. So now I have cis-3-nonene. I have 9 carbons with a 3 double bond that is cis, but I need the 2-methyl. So in the 2 position, I need my methyl. And there is cis 2-methyl-3-nonene. So naming stereoisomers can seem a little bit confusing, but as long as you remember cis, same side, trans, opposite sides, then I find that really helps if you can make sure you remember that. And then remember, at this level anyway, what we're really looking for is the continuation of the chain before and after. Branches coming off a double bond don't count as that chain. You're looking for the longest continuous chain. So hopefully that helps you understand stereoisomers a little bit better, and I'll see you next time.